A confirmation about the audio, please. If you're able to hear me out perfectly well. Thank you. Nitin, why ozone layer wasn't formed in troposphere initially, as we have higher concentration of oxygen in troposphere than stratosphere, and in absence of ozone layer over the Earth's surface, initially whole Earth may receive. That is a good question, Nitin, but understand that formation of ozone also requires a certain degree of lower temperature. The temperature at the region of the ground surface is generally higher. So that is why it is at a greater elevation when the temperature significantly reduces, and then you have a simultaneous action taken by the ultraviolet rays. That is why it is formed in the region of stratosphere. Okay. Now, yeah. So about the temperature distribution in general, if you observe between the layers, I hope we are aware about the fact that the temperature distribution in the region of troposphere, it will reduce up till around minus 80 or 70 degrees Celsius in many of the cases. If you observe this, observe here, this particular chart or figure, this red line indicates the temperature. So at the region of tropopause, it is around minus 60, minus 70 to minus 80 degrees Celsius, depending upon the region and depending upon the season. In the region of stratosphere, observe that the temperature will increase, but at the top layer, the temperature is only around 0 degrees Celsius, but it is a consistent rise. So this is where you come across a negative lapse rate. And here again, it will reduce up till minus 100, significantly to the top of mesosphere. Okay. Now, after this, we come to the factors that cause variation in the level of insolation as is experienced on the surface and as is experienced in different parts of the planet. So what is it that leads to different amount of solar insolation being received? First is the angle of inclination of the Earth. Angle of inclination of the Earth means that, first of all, Earth in itself is not a plane surface. It is a kind of a spherical surface. So even different areas across the different parts of the planet, they will not be receiving the same quantity of solar radiation. There will be a curvilinear path. Then it is tilted further. So that reduces or changes the amount of solar insolation received in different portions. Then you have revolution of Earth around the entire portion of the sun, revolution of Earth in its orbit around the sun. Now the Earth takes a kind of a long elliptical orbit. That means we have a situation of a perihelion and we simultaneously also come across an aphelion, right? So variation in insolation during aphelion and perihelion. Okay. Then you have configuration of land. What is configuration of land? This basically indicates that the direction in which any particular slope is facing. For example, let's suppose you consider a kind of a mountainous area. Now that mountainous region will have two faces, right? Generally. Now, one portion will experience direct rays of the sun, other portion will experience indirect rays of the sun. So that also varies the insolation level in different places. So that indicates the direction of the slope of the land. Then we come across the factor of altitude, that when we move up in height, the insolation level changes. Let us take a look and a deeper look at each of these relevant factors. So we start with the angle of inclination. Now we do know that the planet is tilted on its axis at an angle of 23.5 degrees. That is the tilt on its axis in general. From the vertical, the planet is tilted at an angle of 23.5. And here, observe the solar rays which are coming in. Now here, observe that at different places, the solar rays, they make different angles with the land surface. They make different angles with the land surface. Now, in order to understand their impact in terms of temperature, a very simple experiment would also suffice. So here, think about it. Let's suppose you have the land surface or any particular, let's say, tabletop. Now, on top of it, let's suppose you keep a torch in this position. Okay? The ancient torches that are used by the older generation in general, you'll find the big torches, the steel torches, which if you throw some on somebody, the head will simply break off. Those kind of torches. Imagine that kind of torch you're shining on a table. Now this torch will emit rays and light. Okay, it will be falling upon an area. Now consider subsequently you have a torch which is in tilted position. Now in this case, the rays which are emitted, they would be distributed over this particular region. Now, if I ask you a place A, right? Now that place A will receive greater energy in which condition? In the position 1 or in position 2? What do you think? In which condition will place A experience greater amount of energy? Very good. In the first position itself. In the first position, that is where you have a kind of a vertical concentration of rays, isn't it? So, solar insolation is going to be much powerful, much greater when it is vertical. And when it is slanting, the energy received is generally dissipated because it will have to travel a much larger distance in the atmosphere as well. So much of that solar energy will be moderated by the atmospheric distance that it covers through. That is why when the sun rises early in the morning, it is in a slanting position. It is not virtually and directly overhead. When again, during the evenings, when you observe the sun to be setting, you will observe that sun again is in a slanting position. Again, not a lot of heat. But when the sun is vertically up during the afternoon, during the noon, now at that point of time, significant heating is received. So those areas which experience a vertical falling of the solar rays or a higher angle of solar rays, they receive greater insolation. Those areas which have a lower angle that the solar rays make, the energy received is less. Observe here, angle is very low. Observe here, angle created is larger. So if angle created by the solar rays and the ground surface is larger or is higher, insolation is higher, and hence heating is also higher. Ayush, when we receive maximum heat at 90 degrees, so that is generally around noon, around 12 or roughly between 12 to 1, depending upon which place you are in and what season we are in. That is where roughly around noon you receive the maximum solar insolation and maximum concentration of solar insolation. Then the other factor is the revolution of Earth around the orbit around the sun. Now, here you will observe that Earth takes an elliptical orbit around the sun with the distance which is very variable. The distance is never consistent because it is an elliptical orbit. So, you have the condition of an aphelion during the month of July when it is farthest away from the sun. And you have a condition basically of in January where it is closest from the sun. Now, this also impacts the total amount of solar insolation. During the month of July, insolation received will be lesser. Insolation is lesser. And here, during this time, insolation is higher. Okay, so that is basically, now here you might have a question that you are saying that in January insolation is higher and in July insolation is lower. But in July we experience summer condition, in January experience winter condition. But whenever you have this doubt, always understand that insolation is just one of the factors which influences the temperature. It is not the only factor. Temperature is contributed by many other contributing factors. Then we come across the configuration of land in terms of its aspect, or basically the direction in which the slope of the land is observed. Direction of the slope. Okay, so what is this and why is this relevant enough? So understand this. For example, let's suppose this is the planet. Now let's suppose here we have the position of the sun. Now, in this region, in the northern hemisphere, if I have a mountainous area like this, it will have a northern slope, north-facing slope, north-facing, and we have a south-facing, isn't it? Now, in this position, where do you think you will receive more direct rays of the sun? The southern slope or the northern slope? What do you think? Where is it that you will experience more direct rays of sun to be falling upon the land? Northern slope or the southern slope? Always the southern slope, because the southern slope is experiencing the direct rays of the sun here, isn't it? Now, if I ask you the other way around, let's suppose I have a mountain in the southern hemisphere, it will also have a northern slope, it will also have a southern slope. Now, in this situation, in the southern hemisphere, which will face direct rays of the sun, northern slope or the southern slope? Always the northern slope, right? So that is where the amount of insolation faced is very much dependent on the direction that the slope is basically facing in. This is precisely the reason why the southern slope of the Himalayas, the southern slope of the Alps, all of them, they face direct or they experience direct rays of the sun. And that is why the southern slope of Himalayas, the southern slope of the Alps, they are much more habitable in terms of temperature. The temperature does not plummet significantly to much lower extent in these areas, as compared to the region where you have the northern slope of these mountains. So that is the practical application or the implication of this particular fundamental. Then another factor which comes into play is the altitude. The amount of solar insolation which is experienced, that varies in terms of the altitude. Altitude means the height. So if, let's say, and why is it so? So if, let's say, we consider two different places, one at the sea level, another at a height of, let's say, 5 kilometers, the Tibetan highlands. They are situated at a height of 5 kilometers. Now here, on top of it, you have the atmosphere, isn't it? Now here, if the sun is present in this region, now the solar rays which are coming, solar rays received here and the solar rays which are received here. Now you will observe that the solar rays which are reaching the sea level, they have to encounter or travel through a much larger distance in the atmosphere as compared to the solar rays which are hitting the top of the plateau region. Isn't it? So here, this particular area, in this area, the solar rays have to cover a smaller distance in the atmosphere. Now, what is the implication of it? The implication is very simple. That is, the more distance that the solar rays travel through the atmosphere means greater is the moderation, greater is the vitiation or the diminishing of the solar energy. The lesser the distance that they travel through the atmosphere, more powerful they are. So solar insolation is comparatively higher as one moves up the mountains. This is because closer to the ground, more atmospheric particles come in the path of solar rays. Okay? This is the reason that why when you go up to the mountain, one of the major issues that you face is sunburn. Ideally, when we think about sunburn, we think about it that in the summer season, during extraordinarily greater amount of heating, that is when we get sunburn. But when you climb higher up in the mountains, you will observe that the solar rays are much more powerful. Even though the temperature is low because of different factors altogether. But you will observe solar rays are much more powerful. That is why you will find that the mountaineers, the summiteers or the expeditioners who climb up the mountains, necessarily they have to put on those eye shades or the basic mountain climbing gears or the glasses along with the protective clothing in order to save themselves from sunburn. If the skin is exposed at that high altitude, immediately the skin will be roasted because of sunburn. So that is the aspect of insolation. Now, as I have repeatedly said, insolation is just one of the factors which influences temperature. There are other factors involved as well. So here, let us take a look at few other factors which influence the temperature in a region. So there we come across the factor of albedo. What is albedo? So albedo basically depicts the reflective coefficient exhibited by any surface, the amount of rays which are received and then they are reflected. Obviously, the different surfaces across the planet, all of them will not be able to absorb and will not be able to reflect the same amount of solar rays. For example, if you take the image 1 and if you take the image 2, just by visual perception, if you look at them, which of them do you think will reflect more? The snow-covered and ice-covered peaks or the grassy marshlands? Which of them will reflect more solar rays? Very good. One will reflect more, isn't it? It will always reflect more. So that reflective coefficient is important in order to understand the temperature of the surface. After all, the temperature of the surface is an important indicator of the temperature of the air as well. And that is what is indicated by albedo. So albedo is the portion of solar energy reflected from the surface of the earth back into the space. So this varies between 0 to 1, where 0 indicates complete absorption, and 0 reflection. And 1 indicates complete reflection and 0 absorption. Generally, when we talk about various areas, for example, let's say when we consider the ice covered areas, the ice sheets, and so on, right? Ice covered areas. Now, in these areas, observe that when you have thick ice, in those portions you will observe that almost 80 to 85% of the solar rays, they are reflected back. That means the albedo is as high as 0.85. Okay, albedo is as high as 0.85 here. That means 0.85, if it is the albedo, means what? Means 85% is reflected. And 85% is reflected means 15% is absorbed. Only 15% of that is absorbed. If you consider a water body, or let's consider the image that you have in the form of grasslands or marshlands in general. Now, in these areas of grasslands and marshlands, let's suppose here you have grasses or water, anything. The albedo generally is around 0.25. On an average, I'm taking, it is not the exact figure, on an average. That means 25% is reflected, 75% is absorbed. 75% overall is absorbed in this process. Now, in the first case, 15% is absorbed. In the second case, 75% is absorbed. Out of these two, which one do you think will experience greater amount of heating? What do you think? Ice will experience greater amount of heating or grasses will experience greater amount of heating? What do you think? Okay. So majority of you have given the correct answer. Understand, what is heat? Heat is basically the result of the total energy which is absorbed. In the first case, only 15% is absorbed. So that means there will be lower temperature. In this case, greater amount, 75% of heat is absorbed. So that is where if the heat absorbed is greater, temperature will always be higher. If heat absorbed by a surface is greater, temperature of the surface is also higher. Okay? How many of you have not understood this particular portion of albedo? Kindly point it out. Let me know. How many of us have not understood this? What do we mean by albedo? That is something which is not understood. Okay, fair enough. So I'll repeat it once again, and I will repeat it from the very basics. Pay attention. When we have different surfaces, let's suppose different color. For example, the t-shirt that I'm wearing right now, or let's suppose the skin. Now, do you think each one of them will absorb same amount of light and reflect same amount of light? No. The coloration, the type of material that you have, that many of the times is dependent upon the total amount which is received, the total amount which is reflected. Now, during the summer conditions or during the present season, do one thing. In the afternoon, step outside your house. Now, if your house is, let's say, colored with or painted with a brighter paint, you will observe that the outside walls are still cooler during the daytime. But if you touch the road surface, which is made out of asphalt or black tar, now that will be very hot. Why do you think that is the case? Have you ever thought about it, that why is it that these roads become so very hot during the daytime? That is because they are absorbing. So any material, when it absorbs significant amount of heat, it becomes hotter. Any material, when it reflects greater amount of heat, absorbs little, it is able to stay colder or it is able to stay cooler. Now, think about it, that in a region, let's suppose I have ice surface, and in a region, let's suppose I have water body. Now, ice appears very bright, water doesn't appear very bright. Anything which appears bright, why is it anything that appears very bright? If you think about it, why is it that something appears whitish? Because it is able to reflect all the rays. Why is it that anything appears black? Because it is able to absorb everything. So when we talk about ice, and if we talk about water, now it will be reflecting, it will receive the same light, but both the surfaces will react very differently to the same light which is received. On one hand, while ice will reflect around 80 to 85% of the light received, water will be able to reflect only around 20%. So where is the rest of it? In this case, 100% of light has come here. 100% of light has come here. In the first case, 80 to 85% is reflected. In the second case, 20% is reflected. So where is the rest of the energy? The rest of the energy is absorbed by the surface. So if, let's say, this is the surface, it absorbs 75% of the heat which is received. And the same heat is provided to other surface which absorbs lesser amount. So obviously, when we say that heat absorbed by a surface is greater, temperature of the surface will also be higher. So how do we classify which surface will receive more heat, which surface will reflect more heat? That is classified with the help of albedo. Albedo is basically an indication of the reflective coefficient of any particular surface. If a surface absorbs all of the light which falls upon it, its albedo will be 0. If the surface reflects all the light which falls on it, its albedo will be 1. Okay? But a mere attention to the fact that an albedo can vary means reflective coefficient can vary, also means amount absorbed will also vary. So different surfaces will heat up to different proportion. That is why during the summer days, why do you think it is advisable to wear bright colored clothes during the summer season? Because those bright clothes will reflect the solar rays and you will be cooler inside. During the winter days, it is always advisable to wear dark colored clothes. Why is it so? it will absorb more heat. So you will be warmer inside. So that is the aspect which is also indicated by the Earth's surface. Now, how many of us have not understood? Please let me know. Albedo reflect mode albedo is different for different particular surfaces. Okay, so albedo is very different for different surfaces. So all those who had not understood earlier, please let me know. Got it? Good. That is why, again, I will reiterate, if you stand outside your house during these times, let's say, excuse me, when you stand outside your house during the afternoon time in these seasons, you will experience that if the house is brightly colored on the outside, you will observe that the walls, they are comparatively cooler. You touch the road surface, which is darker, it will be very, very hot because of the coloration pattern. Any surface which is bright is comparatively cooler. Okay. Now, that is also something which can be understood as the implication or as the causation of why in the polar areas we are experiencing an increased rate of melting. In the region of the Arctic in particular, we come across the situation where the melting is initiating or is kicking a process where more melting happens. In a way, it is kicking a kind of a feedback loop where melting of ice leads to further melting of it. How is it? Why is it? Let us take a look at it. So basically, observe this image. Now here, you will observe that those areas which have water which is exposed, now here albedo will be less, so greater amount will be absorbed, less amount will be reflected. In the areas which have a thick ice sheet, more will be reflected, less will be absorbed, isn't it? Now, due to climatic conditions, due to global warming and so on, here let us assume that you have melting of ice. Melting of ice. Now, in the region of Arctic, you don't have land underneath that ice. In the region of Antarctica, you have land, but in the region of Arctic, you only have water body. So when we talk about the Arctic region, so here the ice is melting at a very significant pace. So when the melting of ice happens, it exposes the water, surface. Now water will have a lower albedo as compared to ice. Means what? Water will absorb more, absorbs more heat. Isn't it? Why? Albedo is less. As compared to ice. So it will absorb more heat. Now, when it absorbs more heat, it will increase the temperature. Increases the temperature of the surrounding. Now, if the temperature of the surrounding region, this entirety of the area, if the temperature, let's say in this entirety of the area, the temperature starts increasing, what will happen? It will further fuel the melting of the ice. So in a way, melting of ice is kicking in a process which is going to initiate and further exaggerate the rate of melting. This is being observed due to global warming in the region of Arctic. That is why the region of Arctic is losing ice at almost twice the rate as compared to the other frozen areas. Okay, because as the ice melts, water is exposed, means greater heating, means more melting, means greater water exposed, and that will continue to fuel it until and unless you have a situation where the entire region melts out and the entire region becomes ice free. Is that understood? Good. Now we come to the heating of land and water. Now solar rays or the solar heating is received by both land and water, but then both land and water, they react differently to it. They don't get heated at the same rate. So here, let us understand the basics. What is the factor which will get heated fast and which will get heated more significantly? So we start with Utkarsh, is it possible that Arctic region can melt completely? Yes, as per the IPCC report, it indicates that if the current trends continue, by the year 2040, we will come across at least one such scenario where the Arctic will be completely ice-free. So that is the prediction. That is why you will find that so much geopolitics is being played out about the region of the Arctic, about the control of the Arctic, because once that region will be ice free, it will expose the water bodies, and in those areas you have significant amount of presence of natural gas as well as crude oil. That is why all the various different countries, especially in the Arctic region, they are building vessels, they are building various different machineries in which they can explore and extract oil from the region of Arctic. China has got a different mechanism altogether. China, what it has done, it has declared that in the region of Arctic, we will have a polar Silk Route. So that is where wherever China wants to go, it declares it as a Silk Route. And that is where China says that we have a traditional right to move over the region of the Arctic. And that is why we are developing. Okay, one question. Gayu, tomorrow's class timing is not 10 to 5. Tomorrow's class timing is 10 to 8. So kindly don't get confused. Okay. So could Antarctica be ice free? See, it can be ice free because of continental drift and other factors. But generally, it is absolutely not possible for the entire region to melt on its own in the present position, because Antarctica, the solar insolation is particularly low and it has got a stability of air circulation around it because it is a continental landmass. It is not, Arctic is a water body. So there it is influenced by the nearby air circulation of the various continents, etc. So if there is a kind of a continental movement of Antarctica, then it can come to a tropical region, it can become ice-free. But in its present position, it is very difficult for the entire region of Antarctica to be ice-free. Now here we talk about the region of land and water. Now, here, the solar rays, these solar rays will hit the land also, will hit the water body also. Now start applying logic here, okay? Mentally be active. So here, when we talk about the solar rays over the land, and by water here, I'm not talking about the bucket of water that you keep in your balcony or the small tank that you have outside your house or the small pond that you have in your vicinity or the small lake that you have in your village or the river which is flowing by your place. By water body, I'm talking about oceans and seas. Let me be very specific. Otherwise, I have very frequent questions that you said water will behave like this. I kept a mug of water. It was very hot. So here I am talking about large water bodies, oceans and seas. Okay, larger water bodies. So heat is received by both these areas. In the land surface, if we talk about all these solar rays and all this solar energy, would it be correct to say that in the land surface, all that heat is restricted to the topmost portion only? Around 3 to 5 inches of depth, not more than that? Would it be correct to say that? Good. So here, in the land surface, all the heat is restricted to the top 3 to 5 inches at max. In most of the cases, not even 3 inches. Okay, 3 to 5 inches of land. What about the water body? Now, in the water body, when that heat is received, water is transparent. So, can it be said that this heat will be dispersed into the water? Will it be correct to say that this heat will be going to a depth of around couple of 100 meters, a few 100 feet in general? Isn't it? And the land surfaces, here when we talk about it, the land surfaces, they don't move. In a short term, it is not as if today morning you have woken up, you are in northern hemisphere, and evening when you go to sleep, suddenly you find out that, okay, my land has moved to the Pacific Ocean. Land is stable, land does not move, water moves. Due to various circulatory movements, you will observe that the water is able to move. Water circulation happens in the oceans and the seas. So here, let's suppose a section of water here is heated up. Now, due to circulation, it will move, it will be carried away. So now, can we say all the heat received on that land is restricted to the small area, whereas in that water body, it is spread over a much larger area? It will be pertinent to say. That brings us to the first conclusion and the first aspect of it. So, we can say land gets heated up at a much faster pace as compared to the water body. Anybody having doubt in this particular portion, kindly ask right now, because then we will start developing the concept from here. This is something which we can say, that land here, because all the heat is concentrated and restricted to the only certain portions, only on the surface of the land, so that is why the land will heat up very quickly, whereas water body will take some time to heat up, isn't it? Now, the land has heated up, water has also heated up. Now, in this situation, during evening time, during night time, when there is no more solar rays which are present, so during evening, both of them will lose heat. During the evening time, both of them will lose heat. Now, when it comes to the land losing heat, land will be losing heat only from the top surface where all the heat was restricted, all the heat was concentrated on the surface itself. What about the water body? Water body had distributed the heat and the entire water body had experienced some rise in temperature. So, which one will lose heat faster? The land where it is concentrated in a smaller portion, or the water body where the heat is distributed in a larger area? What do you think will lose heat faster? Land. Land will always lose heat faster because in the land, the heat was restricted into the smaller portions, isn't it? So here, land loses heat at a much faster pace as all the heat is concentrated on the surface. Okay. Now, if these are clear, let's start finding the derivations out of it, the implications of it. So basically, during daytime, when the sun is shining, which will be hotter, land or water? What do you think? During daytime, when the heat is being received, land will gain heat very quickly. So during daytime, land is hotter. During night time, when they have to lose heat, which will be colder, land or water? Which will be colder during the night? Land will be colder. Why? Because the land is losing heat at a faster pace. So because the land is losing heat at a faster pace, that is why during night time, land will be colder. Water is warmer. Isn't it? Now, that is why during nighttime, if ever you have been to a coastal area or a beach region, you would have observed that during daytime, when you go into the water for a swim or anything like that, you will find that the water is cooler as compared to the land. But during nighttime, if you go and dip your feet into the water, you'll find as compared to the land, water is comparatively warmer because water takes a larger amount of time to lose heat. Now, the implication of it in terms of seasons. So, summer season. Summer season is a season of prolonged heating. Winter season is a season of prolonged loss of heat. So, during summer season, which will be hotter? Always land is hotter as compared to water body. Land is hotter as compared to the water body. Whereas during winter season, when there has to be a loss of heat for the entire duration, that is why winter is cold, because that is a cumulative loss of heat which happens every day for the months that we experience winter. So during winter season, you will observe that the land is colder as compared to the nearby water body because the land is able to lose heat quickly. So land is colder, or land is colder, or what can also be interpreted as water body is warmer as compared to land. Okay. So that is the differential rate of heating and cooling of the water body and the land areas in any particular region. Okay. Now, after this, we come across the urban heat island effect. Kajal, heat reduces when it's spread over an area, as is the case with a cup of tea and saucer. Heat reduces when it is spread over an area. That is true. So as in the case, why not the same with oceans? That is the same case with oceans. Heat is distributed in the region of oceans. That is why it takes a much greater amount of time for the oceans to experience a rise in temperature by 1 degree Celsius. Okay, just like as you pour the cup or the tea into a saucer, it expands, the heat is distributed. That means what? That the temperature is lost. Similarly, when you have to heat up the saucer, or in a larger area, if you have to heat the liquid, it will take a longer period of time because heat is distributed. Similarly, in the case of oceans, it takes a longer period of time for the oceans to be able to gain 1 degree Celsius temperature. Similarly, it takes a larger period of time for the oceans to lose 1 degree Celsius of temperature. Why? Because the heat has to be lost cumulatively from all those areas which have experienced that 1 degree Celsius rise. Okay? Now, how do we get cold breeze from sea during the night? We will come to the land breeze and sea breeze. We will talk about it. As of now, please look at the basics if we have understood. As we say, differential heating of land and water impact Indian monsoon. Yes. Now we come to the urban heat island effect. So what is this? Now, generally, you would have observed that when you come to the urban area from a nearby rural region or a nearby suburban area, you would experience that in the urban landscape as you enter, you would suddenly experience a rise in temperature. The temperature rises quite significantly. It becomes very hot in the middle of the urban region. And again, when you go to the nearby villages or the nearby small towns, etc., it becomes slightly cooler. So that phenomena where the urban area is significantly heated up, that is what is also referred to as an urban heat island. So an urban heat island is that part of an urban or a metropolitan area that is marked by remarkably high temperature as compared to its rural counterpart due to excessive human activity. So this is where in the urban area, observe this as a temperature curve. You will observe as compared to the rural, suburban and other portions, suddenly the temperature experiences a spike. Most of us would have experienced this. Temperature experiences a kind of a spike. So that is what is referred to as an urban heat island effect. Now, why does it happen? Why do we experience that spike in temperature? The reasons are simple and straightforward. So here, if you observe, first of all, the urban landscape has got significant amount of concretization which is done. You have darker surfaces in the form of asphalt and rooftops. That means greater absorption of heat. Then in the urban landscape, because of such close vicinity of construction, all the construction in the urban area, you will observe very close proximity, all the tall buildings which are present. That means the flow of air is inhibited. And when there is no wind movement, no air movement, you would have observed that the heat becomes very oppressive. Okay, so that is where less movement of winds leads to lesser heat dissipation. Why less movement of winds? Due to construction activities. Okay, then lack of green cover leading to lesser cooling. Now, when you have a green cover, significant amount of green cover which is present, it provides shade, very significant amount of shade, and that provides a cooling effect associated. But if you don't have the green cover in an area, the land directly gets heated up significantly. So that region becomes very hot. So in the urban landscape, you don't have green cover. So there is significant amount of heat associated, isn't it? So you have one of the reasons is lack of shade. the other reason. Now, the trees, they lose water through transpiration. The leaves that you have in the tree, any tree, when you consider the leaves have got various different pores. Through these pores, they will be losing water vapor through the method that is transpiration. Now, whenever transpiration or evaporation happens, the surface becomes cooler, isn't it? So that is where it becomes significantly and sufficiently cooler. So if there is no green cover, means no transpiration, means no cooling effect. So no cooling effect due to transpiration. Lack of transpiration. Then lack of open soil regions. In the areas, in the suburbs, in the villages, you will find that lot of open areas, grass and soil cover. So there, during the rainfall, water is absorbed and then that water evaporates. Again, evaporation provides a level of cooling on the surface. But in the urban landscape, all the regions are paved or cemented. So there, you don't have that kind of evaporation which is carried out. So that is why it exaggerates the rate of heating. Then greater greenhouse gas emission in the urban areas due to various different methodologies and various aspects of pollution. You will observe that in the urban landscape, there is always greater emission, greater pollution. Excuse me. So due to that, the pollution or the greenhouse gases, they will be trapping greater amount of heat. So more heat is trapped. More heat is trapped. In the urban areas, you also come across greater heating due to the various cooling devices, the various different cooling devices that you have. For example, the air conditioners, the refrigerants, all of them. Now, while they cool the region in the inside, they will provide heating on the outside. If you have ever stood outside the external unit of an air conditioner, you would experience warm winds blowing there, warm winds coming out in that region, isn't it? Now, in the urban areas, you have significant amount of these electrical appliances, these particular cooling devices which function and continuously function throughout the day. All of that provides warming. So what is the solution of it? Solution is to have bright colored buildings, to have better urbanization, lack of congestion should be there. Okay, the building should have enough spacing so that wind movement is observed. There should be construction of greener buildings. What are greener buildings? Not the green color buildings. Green buildings does not mean that you have plants on them. Green buildings refer to those where they are environmentally or eco-friendly, in the sense that they allow the natural light to come in so that you don't need to use the tube lights even during the day, so that there is natural aeration which comes in, which makes the building cooler even during the day. So that is the aspect of those green buildings which can provide a solution. Okay. Fourth point, lack of open soil regions. Open soil regions where you have the grasses, etc., in the rural suburban areas. There, whenever there is rainfall, eventually that is followed by evaporation as well. Whenever and wherever evaporation happens, there is a cooling process involved. For example, let's say you go out into the sun, you perspire, you sweat a lot. But when that sweat evaporates, that is when you feel cool or cooler. When is it that sweat evaporates? That is when you stand, let's say, underneath a fan or in front of a cold air. So that is when the sweat will evaporate. So that is when you feel cooler. So whenever evaporation happens, you feel, or there is a relevant cooling activity which follows. So here in the urban landscape, because you don't have such open soil areas, all that water is drained into the manholes and the sewers. That is where you don't have that large scale evaporation which is observed. Okay. Now, we come across temperature distribution or distribution of temperature across various different parts of the planet and the factors which in a way influence this distribution of temperature. So temperature, as I told you, is dependent on many of the factors. One of those factors is insolation, but not all. Insolation is not the only factor which determines the variation in temperature. So let us understand the various factors which initiate or lead to the variation in temperature in different parts. First is the latitude of the place, the latitudinal position of any particular region on the planet. Now, depending upon whether you are at the equatorial area or the tropical zone or the temperate zone or the polar zone, you will observe that the inclination of the solar rays that varies, isn't it? You will come across the situation where solar rays make a high angle in tropical regions, which means in these areas you have a higher temperature. And in the temperate and the polar regions, for example, in higher latitudes, solar rays are inclined and make a smaller angle. And that is when you have a lower temperature. That is where you will observe that as you move towards the poles, the temperature reduces, and in the tropics, the temperature is sufficiently higher. Then we have the factor of altitude. With the rise in height, the temperature reduces. We have seen that in the case of normal lapse rate. Now, why is it that higher up above the mountain, the temperature is very low? First of all, the air is less dense. So there is less trapping of heat in that region, isn't it? So the loss of heat is very quick. Even though the insulation is higher, the loss of heat is very quick. So that is why higher that you go at greater elevation, temperature is lower. That is why when you move to a hill station, you will observe a pleasant condition of temperature as compared to plain area. Subtropical zone is basically the zone, this area beyond the tropics, roughly between 30 to 40 degrees. That is referred to as subtropics, immediately beyond the tropics, also referred to as extratropical zone. Okay. Gayu, what we have to study after taking these 2-day classes, we'll let you know tomorrow after the classes, because hopefully by tomorrow end we will be able to cover substantial portion of atmospheric phenomena. So you will have a substantial chunk that you will have to revise before coming to the next weekend when we will cover the portion of Indian monsoon. So we'll let you know tomorrow. Okay. Now, distance from the sea is again another factor. How? So when we talk about the distance from the sea, any place, let's consider two different places. So here, let's suppose you consider the Indian subcontinent. Now here, let's suppose you consider a place, Chandigarh. And here you consider, let's say, Goa. Now Goa is right at the portion of the sea, right? Chandigarh is present in the interior. Now here, where do you think that the moisture content will be greater? In Goa or in Chandigarh? Always Goa. Goa will have a lot of moisture content because it is across a coastline. So when you have a moisture content, that means the temperature will be maintained. The temperature will be consistent in the sense that whatever is the heat gained, that will be retained for a longer duration. So in the coastal area, you will never come across extremity of temperature. Whereas in the interior regions, you will always come across extremity of temperature because heat will be gained very rapidly, heat will be lost at the same rapid pace. So here, when we talk about the distance from the sea, first point, coastal regions experience moderation or moderate temperature. Interior regions experience extremity of temperature. Think about it. In the region, let's say, of Mumbai. Now in Mumbai, during the winter season, you will observe that the temperature is around, or during the summer season, the temperature is around 36 degrees Celsius. During the winter season, the temperature is around 15 to 20 degrees Celsius, roughly around 20. If the temperature in Mumbai reduces to 18 or 17, immediately you will find everyone sporting their very nice fancy jackets, having a bonfire, and they will all start complaining that Mumbai is becoming so very cold. It is 18 degrees Celsius. We need to warm ourselves up. But take the case of Chandigarh. Summer temperature 48 degrees Celsius. What is the winter temperature? 2 degrees Celsius, 1 degree Celsius. Right? So there is an extremity of temperature involved. Whereas in coastal areas, never an extremity of temperature will be involved. Now, one of the reasons is the presence of vapor. The other reason is that in the coastal area, you get frequented by the winds coming from the sea, the land wind, the land breeze and the sea breeze, they will frequent that region. So excessive amount of heat, excessive amount of cold conditions, they are nullified by the frequent movement of the wind. Whereas in the interior areas, you don't have such facilities. That is why the coastal areas will always experience moderation of temperature. Okay, you have two reasons for this. One is moisture, presence of moisture means retention of heat means consistent temperature. And second reason, frequent land and sea breeze provides moderation in coastal areas as compared to inland regions. Okay? UPSC has asked this question in the mains examination. Why is it that Delhi experiences such higher temperature range as compared to the region of Mumbai? So this is what needed to be explained. Then you have the factor of prevailing winds. Now prevailing winds, they help transfer heat with the help of advection. So you have advectional process. So in a region, if you have warm winds which keep on blowing, So warm winds mean they will increase the temperature. Cold winds mean they will lower the temperature. So here you have the aspect of cold and warm advection, which influences the temperature. Now, you also have large movements across the oceans. The oceans, even though they appear to be absolutely calm on the surface, they are not calm. Consistently, you will observe that there is an oceanic circulation happening somewhere or the other. Now, these oceanic circulation and oceanic currents, depending on the temperature, we will study in the portion of oceanography about what are ocean currents, what are warm and cold ocean currents. Just understand, similar to warm winds and cold winds, oceanic water also in some places is warmer, it is colder in some areas. Those are referred to as warm and cold ocean currents. So in whichever region you have the presence of warm ocean current, it provides heating. And wherever you have cold ocean currents prevalent, it provides cooling. For example, if you observe the portion in the northern part of Atlantic, you will observe that in the northern region of Atlantic, here you have warm currents. So that is what provides moderation of temperature in otherwise very cold areas. Otherwise, in these higher latitudes, the region would have been very cold, but it is comparatively warmer. Whereas here, let's suppose the cold Peru current, cold California current, cold Venezuela current, all of these are cold currents. So they will lower the temperature. So these are some of the major factors which will influence the variation in temperature in various areas of the planet. Then after that, we come across isotherms. Iso means similar, therms representing temperature. So let's suppose you are given a task that talk about or explain the distribution or variation of temperature across the entirety of northern hemisphere in the month of July. Now what will you do? How will you do that? One way is to write all the cities and write the temperature experience on a daily basis. Now, the other way is to join the various places indicating similar temperature and exhibit the variation in that temperature. So that is what is an isotherm. What an isotherm appears to look like is somewhat like this. So isotherms, these are imaginary lines which join places indicating equal temperature. So for example, let's say place A, B, C, D, right? Let's say E. Now let's suppose A indicates 30 degrees Celsius, E indicates 28 degrees Celsius, B indicates 30 degrees Celsius, C indicates 28 degrees Celsius, and D indicates 30 degrees Celsius. So the isotherm which will join them will be somewhat like this. And this will be the isotherm joining E and C. So this is what is referred to as a 30-degree isotherm, because it joins the places indicating 30 degrees. This is your 28-degree isotherm. So these isotherms are utilized to indicate the distribution of temperature as is experienced in different places. Now think about one particular concept and let me know the answer. Can the isotherms cross each other? Can they crisscross each other? Yes or no? What do you think? Okay. Very good. So, isotherms will never cross each other. They will never in a way cut each other. Why? Because isotherms represent the places indicating same temperature. So imagine if you have a 25 degree C isotherm And imagine an isotherm, 30-degree isotherm, is cutting through it. Now, what about this place? What is the temperature at that place? Is that place going to exhibit 25 degrees Celsius, or is that place going to indicate 30 degrees Celsius? Because both the isotherms are cutting through it. So that is why, because a place can never exhibit two temperatures at the same time, that is why we have the scenario where the isotherms will never crisscross each other. They can never cut through each other. Okay? Isotherms never cross each other. Okay? Reduced to sea level basically means that, let's suppose in the northern part of India you have few mountains as well. So the temperature at the top of the mountain is very different. But if you have to draw an isotherm there, you have to think about it that sea level, what would be the temperature? So you interpolate it in order to able to draw an isotherm. Okay? Now take a look at the isotherm across the globe as indicated in the month of January. Now with the help of this image, we will be able to target multiple different concepts here. So be very attentive here and observe this isotherm. Now in each of these isotherms, you would observe you have 20 degrees Celsius, 10 degrees Celsius, 0. January means winter in the northern hemisphere. Minus 12.5, minus 25. So let's suppose I consider minus 12.5. So that means any place which lies on that minus 12.5 degree isotherm will be experiencing minus 12.5 degrees Celsius. Any place which lies on 10 degrees C isotherm will also experience 10 degrees Celsius, isn't it? Now let us take a look at the heating of land and water. I had told you that, and what is it that we had concluded? We had concluded that in winter, which is going to be warmer, land or water? Or which is going to be colder during winter, land or water? Let me see if we are active enough. During winter, which is going to be colder, land or water? Good. Land is going to be colder. Water is going to be warmer. Let us take a practical implication of it. So observe the region around any of these isotherms. Okay. Let's observe the temperature indicated at this latitude. Now here, we will take a few places. Place A, place B. Okay. Now, let's consider place A and B. B is over Atlantic Ocean, A is over the North American continent. Now, what is the temperature that you will experience at A? Observe the image, look at the isotherm and let me know. What is the temperature that you will observe at A? What do you think? Good. A is where you will experience minus 25 because minus 25 degrees Celsius isotherm is passing through here. So A will experience minus 25 degrees Celsius. What about B? What is the temperature you will observe at B? B will be 0 because you have the 0 degree C isotherm passing through here. So that again proves the fact that during winter season, water is warmer as compared to the land areas. And during the summer season, water will be cooler as compared to the land areas. That is why it is always said that as the isotherms move, or as you draw the isotherms during the winter season over the water body, it is comparatively warmer. So that is why the same temperature, if you have to experience, let's say, minus 25 degrees Celsius over the region of Atlantic Ocean, you have to move further north. if you have to experience 0 degrees Celsius in this land area, if you have to experience 0 degrees Celsius over the water body, you have to move towards the poles, towards the northern portion, right? So that is why the isotherms over the water bodies during the winter season, they are pushed to the polar area because the water is warmer. Now the second aspect, observe the isotherms in the southern hemisphere and compare them with the isotherms in the northern hemisphere. In the southern hemisphere, you will observe that the isotherms are almost parallel to each other. They have a very uniform distribution. Why is that? Because the southern hemisphere is dominated by water body. And if it is dominated by water body, we have seen that the rate of change of temperature in a water body is much more uniform, it is much more homogeneous, and over the land area, it is much more sharp and sudden. Over the water body, because it is a homogeneous region, the temperature changes gradually, slowly, and steadily. Southern hemisphere is dominated by water body. That is why in the southern hemisphere, you will experience a kind of a gradual shift or a change in temperature. This is the kind of thermal imaging of the planet. You will observe that the land areas are particularly colder as compared to the nearby water bodies. Water bodies are warmer. So if you have to experience the same temperature as compared to the land areas, you have to move north in these water bodies or closer to the poles. Whereas in the southern hemisphere, observe there's a kind of a parallelity associated. The change is very homogeneous because there's a dominance of water body. In the month of July, when it is winter in the southern hemisphere, observe again that kind of parallelity exists. And here, observe that the land areas are much hotter as compared to the water bodies. Land areas are much hotter. So if you want to experience the same temperature as the land, you will have to come southwards towards the equator. Okay? So that is the basic concept which is represented by the isotherms. In general, the isotherms are used to indicate the distribution of temperature across the planet. Okay? Now, we come to the factor of temperature inversion. What is temperature inversion? When it is experienced? As of now, kindly please don't get your eyes fixated at the image. Listen to me for a couple of moments, then you will have your entire personal time with the image. You can have one-on-one with the image itself. As of now, listen to me carefully. When we talk about the troposphere, under normal conditions, we experience positive lapse rate. Positive lapse rate means what? That as you start moving higher up, the temperature reduces, right? So under normal conditions, we can say we have positive lapse rate, isn't it? Under normal conditions, that means what? Warmer air is present at a lower region, colder air is present above. That is what is a positive lapse rate. Temperature reduces with height. That means warmer air at the bottom, and colder air at top. Now, warmer air is lighter, colder air is heavier. So in this situation, under normal conditions, under normal circumstances, will we observe a vertical mixing and a vertical movement of air, or will there be a very weak vertical movement? What do you think? Will we observe the vertical movement of air or not under normal conditions? Let me know. Okay. See, even though many of you would be finding it incredibly frustrating to type every few moments, why I am continuously going to ask you questions and it is going to continue throughout is it helps you stay active, at least mentally. And secondly, by this time I almost know everyone who is present in the session. So I get to know that whether you are able to digest it or not. So regardless of how frustrating you might find that every moment of time I'm asking yes or no questions, that is the purpose behind it. So most of you have said that in this case, you will observe or come across vertical movement of air, right? Now that vertical movement of air, vertical movement, that vertical movement of air is very important in terms of mixing of the pollutants which are there, mixing of the various different air particles which are there. As the warm air will rise up, it will cool down and it will lead to the formation of clouds due to condensation. It will bring about rain. So here, this air is not stable because the warmer air will want to rise up, colder air will want to sink down. So this condition is what is referred to as instable or unstable air. Brings about mixing or brings about mixing of air. Normal conditions mean day-to-day conditions. Under everything which is normal, that is normal condition. Okay, brings about mixing of air, causes rainfall, due to clouds, due to cloud formation, etc. But due to certain atmospheric phenomena, due to certain conditions and criteria, we come across a scenario where the colder air is closer to the ground surface and the warmer air is trapped on top. Now, that is a condition where a negative lapse rate is achieved. And under the conditions of a negative lapse rate, when we have inversion, you have a negative lapse rate which is achieved. Now, under the conditions of a negative lapse rate, what do we have or what do we encounter? Due to certain conditions or the other, why this happens, we'll come to it. Due to certain conditions or the other, the warmer air is trapped above a colder region, an air which is cooler. Now, warmer air natural tendency is to rise up and the colder air's natural tendency is to sink. But here it is already at the bottom. Where will it sink? Will it dig a hole and go into a mine? No, it cannot sink any further. And in this case, warmer air, it is already above. It cannot rise in any further. So here, the air is stable, no movement. So this is the condition of stable air. That means no movement. No movement means what? No movement means whichever pollutant is present, that pollutant stays there for a very long time. No cloud formation will take place. No rainfall will happen. So that is the condition which we refer to as temperature inversion. So broadly speaking, when we say or when we talk about temperature inversion, it is the reversal of the normal behavior of temperature in the troposphere. Temperature inversion is quite common but happens for a shorter duration due to various activities and various events. An ideal situation for inversion is still air, long winter nights with clear skies. Why? We'll come to it. It is a normal phenomena throughout the year over the polar areas. Now, depending upon why this temperature inversion happens, where it happens, and when it happens, it is subclassified or divided into various categories. So here, it is of various categories, that is surface inversion, then you have upper air or subsidence inversion, then you have what is referred to as frontal inversion, and then also we have the valley inversion. So why this happens? What is this surface inversion? In all these conditions, one thing which is very common is colder air is present on the ground and warmer air is above the colder air. Colder air. Let us take a look at all these different kinds of inversion and let us try to understand why they happen, when they happen, and what is the conditions required. So we start with the surface inversion. That is inversion happening due to the surface condition. So this is, in broader terms, understand inversion due to surface. Now, how is it that the surface will lead to inversion? We do know that the temperature of air is directly dependent on the temperature of the surface. After all, conduction is an important methodology of heat transfer. So if the surface is warm, air above it will be warm. If the surface is cold, air above it will also be cold, isn't it? So inversion due to surface, so surface impacts the air temperature due to loss of heat, or due to rather conduction. Okay, now let us understand it carefully. Okay, kindly pay attention for the final few moments. Once you understand this process, you will never forget it. At least that is the hope. Now here, let's consider a region which gets very cold during the night. Okay, because please understand, in this case, it is the ground surface which becomes very cold. Inversion is what? The air near the ground is colder than the air above it. So, and by the way, a general question, most of us, I think, most of us, I assume, we would have completed our 8th standard, 9th standard. So we do understand what is insulator and conductor. Air, is it a good conductor of heat or is it a bad conductor of heat? What do we think? Is it a good conductor of heat or is it a bad conductor of heat? Air. Okay. Let me rephrase what is a good conductor and what is a bad conductor. A good conductor is the one which is able to transmit heat very efficiently from one region to the other. A bad conductor is the one which does not efficiently transfer heat from one end to the other end. Okay? So now if you think about it, when you have a solid metal, it transfers heat very efficiently from one end to the other. Now again I ask you the question, air, is it a good conductor of heat or is it a bad conductor of heat? So one of these days I have to stop asking these questions in order to maintain some sanity. Air is a very bad conductor of heat. Air doesn't allow the transfer of heat or doesn't allow the movement of heat efficiently. Heat is dispersed and trapped here and there. Solids are generally, metals are good conductors of heat. Air is a bad conductor, does not transfer heat very efficiently. For those of us for whom it is a new source of information, note it down somewhere. Otherwise, I hope most of us are aware of it. So here, when we talk about, let's say, a region like Delhi, or we were talking about Chandigarh, let's talk about Chandigarh itself. Now, during the winter months, winter season, let's say the 1st of January, when it is very cold. Now, let's say at 5 p.m., temperature is roughly around 12-14 degrees Celsius, right? Let's say the temperature is 12 degrees Celsius of the ground surface. So the temperature of air immediately above it, roughly similar. So temperature of air, 12 degrees Celsius here. Let's suppose as we go slightly higher up, you have variable amounts of moisture which is present. Let's suppose higher up the temperature is 7 degrees Celsius. Let's suppose higher up that you go, the temperature is 2 degrees Celsius, and so on. Now, during night time, it will lose heat significantly. Because when the sun is not shining, that is when the ground loses heat in the form of terrestrial radiation. So let's say we consider 4 a.m. in the morning when it is grudgingly cold, right? Especially in the northern parts, it is very, very cold at that point of time. The temperature of the ground surface can be as low as 2 degrees Celsius. Now, because the air immediately above is in contact with the ground surface, the air will also exhibit somewhat of a similar temperature, 2 degrees Celsius. Now, why is it that from 12 it has suddenly become to 2? Because the ground has become colder. It is not that the air has lost heat. It is because the ground has become suddenly very cold. Now, above it, in this region, will that also experience the same loss of heat? No, because it is not in contact with the ground surface. It will cool down, but not at the same rate. Let's say it cools down and it becomes 3 degrees Celsius. Above this, it also cools down. And let's suppose it becomes minus 2 degrees Celsius. So here, you will find that you have a warmer air in comparison. And here you have cooler air. A condition of inversion. Now, why that inversion has happened? That inversion has happened because the ground surface has cooled at an extraordinary rate. Isn't it? Had the ground surface not cooled at an extraordinary rate, there would not have been that low temperature. Again, I will explain and again understand it. All of those who have not understood this, understand this. Okay? And listen to this carefully. So, we have seen that the temperature at 5 p.m. is around 12 degrees C, temperature of the ground. Now, air is in contact with the ground surface. Now, temperature at 4 a.m., will it be lower as compared to 5 p.m. or will it be higher as compared to 5 p.m.? It will be much colder, much lower. Early in the morning, 4 a.m., it will be very, very cold. So at that point, let's take the case now temperature becomes 1 degree Celsius, let's suppose. Temperature of the surface. This is the surface temperature. Surface temperature. Now, the air is in direct contact with the surface. So due to conduction, the air closest to the ground surface, which is in contact with the surface, that air will also become colder. So that air will gain a temperature or will exhibit a temperature of 1 degree Celsius because of being in contact with the ground surface. If my hand is at 1 degree Celsius, the air in contact with that hand will also gain it or will also exhibit a temperature of 1 degree Celsius, right? But above it, that same loss of heat won't be experienced. Why? Because at this region of the ground surface, it is the contact which is reducing the temperature. If there is no contact with the ground surface, why will the temperature reduce so much? So let's say higher up that we go, from 7 degrees Celsius at this altitude, also temperature has been lost. Let's say it becomes 4 degree or 3 degrees Celsius. Here it becomes 0 degrees Celsius. So there is a loss everywhere. But the loss is more drastic where? At the ground surface. Because the ground surface becomes suddenly very cold. Surface loses heat suddenly. So that is when you observe the conditions of inversion, because this is comparatively warmer. So this will happen when the surface loses tremendous amount of heat suddenly, not over a long term, because over a long term, if heat is lost, the upper air will also be able to lose heat. Suddenly, during the night, the temperature plummets. And when does that happen? When you have winter nights. Winter nights are longer as compared to summer nights, so more time to lose heat, right? Now, when is it that heat is lost more efficiently? If you have, if you consider, let's say, the ground surface, if you have high level clouds. Now, if there are presence of clouds, these clouds generally they will trap the terrestrial radiation, they will reflect it back, and they will provide heating. So that is why cloudy nights are generally warmer as compared to clear nights. So when you have a clear sky, loss of heat is much more efficient. Okay? So long winter nights and clear sky, when it is observed, surface inversion is observed. So here, a surface inversion occurs when the atmosphere at the Earth's surface is colder than the air above it. Around sunset, the ground cools rapidly by radiating heat upwards into the space. The air in contact with the ground cools by conduction, causing the lowest layer of the air to be cooler as compared to the higher air. This is generally observed permanently in the polar areas, but in the higher to middle latitude also, where the winters become very severe. In India, especially in the northern portion, you experience this. Southern part of India, you don't experience this because it is perpetually warmer. So in the southern part of India, I hope we are clear that we don't experience a distinct summer season or distinct winter season rather. That is why you don't have that sudden cooling. Then we have other kind of, now I hope all of us have understood the surface inversion, right? Now we come across the upper air or subsidence inversion. This is observed in the winter nights in the middle to higher latitudes. Winter nights, middle to higher latitudes, not observed in India. Middle to higher latitudes. Not observed in India. Generally observed in the European region. So what is this? Subsidence means something is sinking, something is subsiding. So just so that you are not disturbed by the image, because mostly when we take a look at the image, our mind is towards the image and the text itself. So what is this subsidence inversion? So here, let's suppose we take the ground surface. and we are talking about the middle to high latitude. High latitude. Now that too, when during winter nights. Winter nights. Now, the ground temperature in the middle to high latitudes during winter nights, what will be the ground temperature? Very low, right? So, very low ground temperature, low temperature, and other than the very low temperature which will be observed, the air above it will also start becoming cooler. Colder air by virtue of being in contact. Generally, when you have colder air, the air above it is also going to be much colder, and so on, positive lapse rate. But in certain areas, we have a situation where the air starts subsiding due to atmospheric circulation, which is initiated. In certain areas, we have sinking air column, right? Let's suppose we have a cold air parcel. Let's suppose in a region, you have a cold air parcel. Now, cold air parcel is generally heavier. Now, heavier air parcel will indicate a what? A sinking phenomena. A sinking phenomena. Now, will it be correct to assume that this air is moving into a region of greater air density slowly and steadily? It will be a correct presumption to make, right? Now, when it is moving into a region of greater air density, what will happen to this air parcel? It will experience a kind of a compression, isn't it? It will experience a kind of a compression. And that compression will lead to what? It will lead to adiabatic heating, isn't it? So it will lead to compression, will lead to adiabatic heating. Right? So this air becomes warmer, whereas this air is colder. Now here the inversion is achieved. Why? Had this air not been sinking in that region, or had there not been a subsidence of air in that region, there would not have been any inversion. But here you are experiencing an inversion because there has been subsidence of air, isn't it? So that is why this is also what is referred to as subsidence inversion. Not observed in every place in the middle and higher latitude, not observed across the planet. Only in certain specific areas where due to air circulation, you have an air which is forced down. Due to air circulation, some areas have an air which starts sinking because of colder conditions. And that is when, as it starts sinking, it starts warming up. And that is where you have a warmer air which is trapped on top. And this is what is upper air subsidence inversion. So here observe, descending air is compressed and it warms adiabatically, whereby in the lower stretches, because of low temperature, winter months, middle to higher latitude, ground will be very colder. So when a widespread layer of air starts descending, it leads to subsidence inversion. The resulting increase in atmospheric pressure leads to heating and compression, right, of the air above. So that is the factor of subsidence inversion. Now, this inversion type can stay in the same place for a very long duration. Subsidence inversion once created, unless and until that circulation of air is disturbed, that circulation of air is disrupted, it will stay in that place for a very long duration. And it is where, tragically, you had the very infamous accident of which happened in London in the early 1950s what is also known as the London smog. Smog is basically when smoke gets mixed with fog. So in the case of winter months in London, you had the formation of this upper air subsidence inversion. And that meant in the early 1950s, you had a lot of coal which was burnt in domestic households and industries. That meant all that coal burning and all the fossil fuel burning stayed in the lower level for a very long time because there was no mixing due to inversion. And that meant many people inhaled that, many people were hospitalized, many people lost their lives as well. Okay, now we come across frontal inversion. Now, fronts are something that we will study tomorrow, what fronts are. But basically, fronts indicate a transition zone between colder air and a warmer air. So this is basically fronts indicate a transition zone between colder air and warmer air. Okay, so colder air, now think about it logically. Colder air will have a greater volume or warmer air will have a greater volume in terms of the volume of the air parcel or any air column. Colder air will have a much more expansive volume or warmer air will have much more expansive. Good. Majority of you are correct here. So colder air, whenever air is cold, the particles are very close to each other. So whenever colder air is present, it will have a smaller volume. Warmer air, on the other hand, will have a much more expansive volume associated. Warmer air. And this is colder air. Now, in the cases where the warmer air and the colder air, they interact, colder air has got a much concised and a compressed volume of sorts because the particles are present in greater density. So when they move, warmer air starts climbing up the region of colder air like it is an inclined plane. So that is where after some time, you will observe that the warmer air has simply climbed up this particular region. Observed again in the middle latitudes. Middle latitudes mean around 35 to 55 degree north and south. Middle latitude, around 35 degrees to consider 60 degrees north and south. Okay. Now here, warmer air will start climbing. Why? Because it is expansive. The molecules are moving far away from each other. They have greater energy. That is why. So in this region, if you consider any particular area, if you consider cold air is at the bottom, warm air is at top. So this is a condition of inversion. This is what is frontal inversion. When we talk about fronts tomorrow, you will understand more about this particular aspect. Then we come across the final kind of inversion. That is what is referred to as the valley inversion. This is observed at the valley bottom. At the valley bottom, where you have narrow valleys at night. Okay, how this happens and why this happens. So basically, observe this. If let's suppose you have the mountainous areas and this is the valley. So in the during the night time, every place will lose heat quite sufficiently, right? At quite a rapid rate, every place will lose heat. Now, if I ask you, place A and place B, which would be losing heat more rapidly? A or B? What do you think? Which will lose heat more rapidly? Okay. Why do you think B will be losing heat more rapidly? Any of you, if you can enlighten me with the reason? Why do you think B will lose heat more rapidly? It is a surface. This is a mountain, my dear friend. This is a valley. A will lose heat much more rapidly. Why? Because the air above it is much more thinner. So there will be lesser trapping of heat. So that is why A loses heat rapidly, more rapidly. Because the air above it is very thin. It will not be able to retain heat. Whereas above B, the air will have greater density. So it will be able to retain significant amount of heat. Now, that means the air above A will be cold, here also cold, and the air above B, that will be comparatively warmer air. Now, which is heavier, colder air or warmer air? Warmer air is lighter, colder air is heavier. So automatically, due to gravitational pull of attraction, this colder air, that will slide down the slopes. It will slide down the slopes. It will uplift or uproot the warmer air, and this warmer air will be forced to move slightly upwards. So at the valley bottom, what is it that you observe? At the valley bottom, colder air from the top replaces the warmer air of the valley. Right? So that is what leads to a condition of inversion in the valley. That is why in the case of narrow valleys, it is always said, never ever take shelter at the valley bottom during the night, because the temperature will plummet suddenly due to cold winds sinking from the mountain tops. That is why many of the times you will find that in the case of a narrow valley, the base is absolutely devoid of any kind of agricultural plants, fruit or flowers. It won't be found, because during the night, sudden frosting will happen. Whereas if, let's say, this valley would have been broader, very broad, for many, many kilometers, then this impact won't be observed. If, let's say, this cold air finds a kind of a passage to drain away, it would not have formed this kind of inversion. But if it is a narrow constricted valley, it will always lead to plummeting of temperature. That is where it is referred to as a valley inversion. Okay? Now, here, let's take a couple of questions before I will end the session. So here, taking the first question, normally, the temperature decreases with the increase in height from the Earth's surface because the atmosphere can be heated only upwards only from the Earth's surface. There is more moisture in the upper atmosphere. The air is less dense in the upper atmosphere. Why is it that the temperature decreases with the increase in height from the Earth's surface? Nitin, there will be some amount of adiabatic heating, but the air will be very, very cold. So even after that, it will still be very cold. We have discussed this question quite significantly well. So I don't think we should have any difficulty in this. Good. Majority of us have given the correct answer. So the atmosphere can be heated upwards only from the surface. That is correct. There is more moisture in the upper atmosphere. Incorrect. That is not true. Moisture is restricted, or water vapor is restricted to the lower levels. And the air is less dense in the upper atmosphere. That means lesser retention of heat, hence colder conditions. So in this, 1 and 3, that is going to be correct. Then the annual range of temperature, that is the annual variation in temperature in the interior of the continent, that is between the summer and the winter temperature, the range is high as compared to the coastal areas. What is or are the reasons for that range in temperature? Thermal difference between land and water, variation in altitude between continents and oceans, presence of strong winds in the interior, heavy rains in the interior as compared to the coastline. So annual range of temperature in the interior is high. That is, the temperature between day and night is high in the interior, or temperature difference between summer and winter is high as compared to the coastal areas. Coastal areas have moderate temperature. What is the reason? Fair enough, Mayank, even if the answer was visible, I understand. But then, yeah, I hope that most of you have given the correct answers. I will still assume by application of logic. So here, thermal difference between land and water, different rate of heating and cooling brings about land breeze and sea breeze. Variation in altitude between continents and oceans. That is not the case. Many areas in the interior are at the same level as compared to the oceans. Does not mean a variation in temperature. 2, if you eliminate, you will automatically reach the correct answer. So presence of strong winds in the interior, that is not the case. Winds will be more stronger in the coastal areas. Heavy rains in the interior as compared to the coastline, incorrect. It is the coastal areas which will experience greater amount of rainfall. So that is where we'll end the session for today. Tomorrow when we meet, we will talk about the atmospheric circulations, the wind patterns, atmospheric pressure, and we will continue thereafter. Okay? For nearly 2 days, which never happened. Is there anything? No, Dinesh, that temperature drop that you are talking about in Chennai, that was largely related to the La Nina conditions, which brought about a significant amount of rainfall and cooling activity. That is why. Inversion, surface inversion will be observed in areas where the nighttime temperature drops to around, let's say, less than 5 degrees Celsius, which is observed across the northern part of the country. Okay. So till we meet again tomorrow, take care of yourself. Goodbye. Have a good night and thank you.